Hi guys, this is your TA Mohammed Ubaidullah. I'm here to actually explain a little bit about Lab 3A of COE 608. So this lab is about designing 32-bit ALU, and as you can see here, the purpose of this laboratory is to implement and test the 2-bit ALU. So ALU is actually arithmetic logic unit. It is the brain of the CPU. If a CPU is a brain of the computer, then ALU is the brain of the CPU. Basically, it does arithmetic and logical operations. So arithmetic operations are arithmetic operations would be something like addition, subtraction, multiplication, division, and other logical operations would be or operation, and operation, and then XOR. These are some kind of logical operations, and then there's ROR, which means roll over right, and then roll over left. So in this lab, something which is new to you guys is ROR and ROL. These two operations are new to you. OR and XOR and addition, subtraction, multiplication, division, you already are familiar with them. But ROR and ROL is actually a concept which is new in this lab. So let's figure out what ROR or ROL is. ROR stands for roll over right, and in this lab you will see that we have it is mentioned at the bottom that this ROR, ROL and ROR operations are logical shifts, not arithmetic. There's a difference between logical shift and arithmetic shift. These two are actually shifts. So ROR is roll over right. So for example, you have some bits here. So I will write this number in binary. 0B means I'm writing the next number in binary. 0 0 0 1 0 1 0, something like that. So this is 8 bits. If I want to do ROR1 time ROR1, which means that I will shift all of these bits one position to the right. So then after ROR, the bits will look something like this. So right is that way. So 0 0 0 0 1 0 1. So what happened was all of these bits were shifted one position to right. So this one goes in there, and then that one goes in there, this 0 comes in here, and there this was an empty place. When you shifted the bits, this was empty place, and we placed a 0 there. When we place a 0 in place of the empty place, we call it a logical shift. If we place 1 or 0, that is arithmetic. So we are not concerned about arithmetic shifts or arithmetic shifts right or left. We are concerned with logical shifts. So then there's another ROL. ROL means roll over left, and same case here. If we have a number something like 0 0 0 and 1 0 1 0, so after I do roll over left one time, which means that all the bits will shift to left one positions. So here there will be 0 0 0, and there here will be 1 0 1, and then there will be 0 0. So what happened was all of the bits moved left one time, and then there was an empty place here, we placed a 0 there. So this is logical shift. So why do we need to study these two operations, or why is it necessary to implement this in ALU? It's actually very convenient for us to implement these two functions because it makes computers easy to multiply numbers. For example, this number in binary, this one here is actually remind me again, this is 6, I think. So 2 to the power 0, 2 to the power 1 is 2, 2 to the power 3, 2 to the power 4, 2 to the power 4 is 8, and 9 tenths, so this is 10. Okay, so 10, and when we shifted right, what happened was, what is this number now? That is actually 5. So when we shifted one time to the right, the number actually got divided by 2. Isn't that true? Then when we shift it to the left, the number actually, this was 10, and this here actually is now 20. The number actually got multiplied by 2. So shifting to the left is multiplying by 2, or one time is multiplying by 2. Shifting to the right one time is actually multiplying by, dividing by 2. So for example, for the general rule, so generally if I want to do, if I have a value and I perform a roll over left n times, it will give me value multiplied by 2 to the power n. So the number of rolls I do is 2 to the value gets multiplied by 2 to the power of that number. So and again, value ROR, if I shift it to the right by n positions, the value actually divides by 2 to the power n. So again, let's take another example for so let's do 0 B 0 0 0 0, and then we have 1 0 1 0. That's 10 in binary. And then we have let's do roll over left, and then let's do it 2 times. So this bit goes to here, and then this bit goes there. Similarly, all the bits move 2 positions to the left side. So here I'll have 0 0 1 0 1 0 0 0, and similarly these 2 zeros are added. So 10. Now what is that number? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 2 to the power 3 is 8. 8 plus 2 to the power 5. 2 to the power 5 is what? So 2 to the power 5 is 32. 32 plus 8 is 40. So this number is now 40. So what happened was, the original value got multiplied by 2 to the power n. So what that means is 10 multiplied by 2 to the power the number of shifts, which we did 2 here, so 10 multiplied by 4, that's 40. So by just shifting the bits, we are actually multiplying the number by the powers of 2. Now this is actually very interesting for us in ALU, because if we want to do multiplication, for example, we want to do 5 times 2, let's take 3 or 4, let's take 4. So if we want to do 5 times 4, a computer who is not capable of doing multiplication directly could do something like 5 plus 5 plus 5 plus 5. So in one clock cycle it might add 5 plus 5, and then it gets 10 plus 5 plus 5, and then in another clock cycle it adds 10 by 5, and then it gets 15 plus 5, and then in another clock cycle it adds 15 with 5, and then it gets 20. So one CC clock cycle, one clock cycle, and then one clock cycle, and then one clock cycle, the last one. So it took about 4 clock cycles to calculate the answer to 5 multiplied by 4, because of this 4 number here. What if it was 5 multiplied by 20? So it would take 20 clock cycles to multiply that number to get the answer. So isn't this easier, that if you just shift, and computers can do shifts in 1 clock cycle, so when you want to do 5 multiplied by 4, you could just shift the bits to 2 positions to the left, and what that in programming we write it like that. So 5, shift the bits by 2. So this is shift roll over left, logical shift left. So that will result in 5 times 4, right? What if now the questions you might be asking is that what if we don't have an even number there? For example, we have 5 multiplied by 5. What about that? So the easy answer to that is, first shift the bit by 2 and then add 5 to it. So that would take less cycles than 5. So this takes 1 clock cycle, as you know, shifts take 1 clock cycle, and then addition again takes 1 clock cycle. That takes 2 clock cycles. That's it. So when we do 5 shift by 2, that will result in 5 multiplied by 4, and then you add 5 to the answer. That is the answer of 5 multiplied by 5, which is 25, right? Similarly, if we have something like 5 multiplied by 7, what to do there? So what you could do is 5 shift 3 times. When you do shift 3 times, remember the thing is 2 to the power 3. So you are actually doing 5 multiplied by 8, right? So what you are doing here is actually 5 multiplied by 8, right? By shifting the bits 3 times to the left, you are doing 5 multiplied by 8. So how do you get 5 multiplied by 7? You minus original number from it, and then you will get 5 multiplied by 7, 35. So this is how computers actually accelerate their multiplying power. They shift the bits left or right, and then they subtract or add the whatever the problem or the difference is. Alright, so let's go back to the lab manual and see what we are required to do in here. So the A comes in. A is 32 bits, B is 32 bits, and we have a ALU operation selection. So the ALU operation selection is something like, if you have a calculator, you input the first number and then you press addition, multiplication, or division. That is actually ALU operation. And then you press enter the second number. Then when you press equals, that gives the result. So this is ALU is basically just like a calculator. And then you have a zero flag. Flag actually usually represents a 1 bit. So 0 is 1 bit and carry is 1 bit. 0 suggests that the output of that whatever operation you did, the output or result of that was complete zeros. So result all 32 bits will be 0 0 0 0. When that condition occurs, 0 flag will be 1. And then carry is something like if you have an overflow or something, 32 bits you added with 32, and all of that resulted in a carry, which means that it has the result is not 32 bits, the result is 33 bits. For example, in mathematics, if we, in simple decimal terms, if we have 6 and 5, you see this is 1 digit, this is 1 digit, but if you add them, 6 plus 5, you have 11. This is not 1 digit, this is 2 digit. So this, you can say that this is a carry, right? Carry to the next state. For example, if I have 16 and 15, if you add that, then you will have 11 and 1 goes to carry, right? So that actually means that is a carry. And in that lab, this is actually that signal, so that the operation actually resulted in a value which is higher than 32 bits. So you should take care of that. That all is explained here, what I just explained. And then your device will be this, and when I will be coding in this video, I will not be using that device. You have to take care and use this device or whatever device you have, because I have a different device than that. So we are required to do ALU operation. It should be AND, logical, add, subtract, ROL, ROR, and remember this, that you are here, it says operation should be performed using structural approach. I will explain what that means. Is that is A statements A plus B, A minus B, VHDL statements are not acceptable. So I will explain that in a little bit. And the key here, when you read this line, and if you are a little bit familiar with the ALU and how addition and subtraction is actually used, you will find out that 2's complement, the subtraction should be performed in 2's complement. That is, A minus B is actually equivalent to A plus not of B plus 1. So what that means in logical terms is, okay, so if you have a value A and if you have a value B, and then you have a adder, and then you have sum, which is the result, right? So if you want to do a plus b, that is simple. You just feed it into the adder, a value, b value, and then adder also has carry in, which is the carry from the previous stage, and then it will do the addition and give the result, right? So in this case, when you're doing a plus b, c in should be 0, right? There's a reason why every adder has a carry in, even though there's no previous stage. For our adder, there's no previous stage from which the carry could be coming in. We need that to implement in subtraction. I will explain that in a bit. So this is C out, which is carry out for the next stage if we have it. In this case, we don't have it. So anyways, so this is how you implement addition. In subtraction, as it says in the lab manual, what you can do is you have the same adder here. So you have the same adder here, you have sum, and you have the carry out, right? So what you can do is actually not gate, add a not gate to the A, and then A comes in as it is, and then you feed that in to the B, and then in place of C in, you type in, you put 1. So what this means right now is that A plus not of B, and then plus 1, right? This is what you implemented here, and that is equal to A minus B. So if we go back to the lab manual, what we are required to implement, A plus not of B plus 1, right? That is exactly what we implemented using the same adder. We don't need to implement a subtractor unit. We just need to use the same adder, but just make the C in 1 instead of 0, make it 1, and then not the B. So in order to detect whether you want to do addition or subtraction, remember we have these control lines in there. So we have these control lines in there. In order to differentiate between addition and subtraction, there's this most significant bit. So if the most significant bit is 0, we do the addition. If the most significant bit of the ALU operation is 1, we do subtraction. So we need some kind of device which can either, if it is 0, it will feed into the adder normal B signal. If it is 1, it will feed into the adder the not signal of B. So what is that component? Simple. That is a multiplexer. So if I add another page and do, so our circuit basically becomes B, and then you have this is normal B, and then you have a not gate there. So this is either 0 or 1. This is the most significant bit, and then this actually feeds in to the adder unit. So here we have our adder, and then we put in A there, and then we put in B there, and then the carry in, C in, I drew it like that because I needed it. That will also be most significant bit. If most significant bit is 0, which means that it will be B will be going in through the adder to the B part, and if most significant bit is 1, then not of B will be going through and going through the B, and C in will also be 1 because most significant bit is 1. So that way you can implement both addition and subtraction using the same adder unit. So this unit we can use the same. We don't have to make 2 units of this and then implement it. So other things which I want to discuss which are important in this lab is some insight into the this lab actually requires you to implement things structurally, which means that you need to take care of the design abstraction part, which means that you don't make a simple ALU using if statements in one entity, that's it. No, you have to make it structurally, make 1-bit ALU and then connect it together to the other ALU to make 2-bit ALU. Similarly, in the lab you are required to do 32-bit ALU, so you need either you can connect many 1-bit ALUs together, 32 of them, and then make a 32-bit ALU, or you can actually connect 4 of them together, make 4-bit ALU first, and then use many of 4-bit ALUs to connect 32, make 32 bits ALU. So the example, this is just talk. Let me actually implement it in front of you, and so that you can see what is going on and what I'm talking about. So let us make a new project. Directory to be something else. Okay, so let me make a new folder here. Lab 3A. Okay. Yes, empty project. I don't want to add any files. And guys, this I am selecting any other device. You have to select your own device. And by the way, this number, this device number, you can read it on your chip. So I'm actually reading it on my FPGA chip. C6. That is my FPGA, but you can select your own, whatever is in the lab, wherever you're doing this. As we have done it in the first lab, none, none, and finish. Alright, so you might have some different menus because I have the latest version of the quarters, but you know how to switch from hierarchy to files. So here you can see I like to switch it to files, and then you can see all the files which I have. So I'll make a new VHDL file as in the lab 1, and then I'll write some code in it. Alright, so I just copy pasted my code in here. So this is, I have called this entity a simple ALU. So this part is an entity in which you describe what the input and output is of the entity or of the component. You can say a device, whatever you're designing, inputs and outputs. So inside the entity you describe what are the inputs, what are the outputs. You don't care for now what is inside. In the architecture you care about what is inside, what is happening inside with those inputs and outputs. So here we have a simple process which depends on A, B and operation. Operation is our selection. Remember in the lab manual we have this one, ALU operation. That is exactly what I mean by operation in there, in here. So result is the output, carry out is the carry out, zero signal is zero. So this is zero flag, it's STD logic, and these are vectors. So the operation is actually 3 bits. Remember, see why 3 bits? Because of this, and also because of this 0 0 0 0 0 1 0 1 0 1 0, right? So you get the point. So this is a simple way to implement ALU. When it is 0 0 0 and there is and these two, and put it, assign it to result. When it is 0 0 0 1, or it, when it is 0 1 0, and it add it, or and all of this. This is a simple way to implement ALU, but we don't want you to do it this way. When I compile it, let me save it by that file, simple ALU. Alright, so while it is compiling, let us discuss something about this. So this is the way you could do it, but we do not accept this. You won't get any marks for this. Let me see what the errors are. Oh, so sometimes you get this error, set it as top-level entity and then just compile. because our project name is at 3A and there's no file named at 3A. So simple ALU, if you right click on it in the files view, remember to be in the files view, and then whatever entity you're compiling, right click and set as top level entity. In this lab you will understand why we need to do that. In lab 1 and lab 2 you were doing it blindly, but right now you need to understand what is the meaning of set top level entity, right? So set top level entity basically means that this is my main entity. Other files are just supporting this file, or they are include files, as you can say in programming terms. This is where my main function is. Remember, in programming you used to type in one of the C files you had the main function, and in other C and H files you describe your classes and all that. Exactly the same way here. Top level entity is actually where your main function is, and the other files, that those are just includes and other stuff which you need. So this is the simple way to do it. But the other way we want you to do it is that you design a 1-bit ALU. Okay. You design a 1-bit ALU, and that will have sum, that will have a carry out, C out, that will have a carry in, C in, output, output, input, then that has A, that has B. So this is a simple ALU. I think you have learned this in the digital systems, but I'm just going to reiterate it. I think you know what this is. C out. This is also called as full adder. If you search online how to what is the VHDL code for full adder, you can download that and use it in your lab. So this is the full adder. So if you draw the truth table for it, I think you have already done this. I'm not going to do it here, but the basic term is that basic gist of it is that C in plus A plus B is the sum, and then if there's some carry out, that carry out signal will be 1. So all of this right now is 1 bit, 1 bit, 1 bit, 1 bit, 1 bit, 1 bit, right? So what we need in the lab is actually 32-bit adder, right? So how do we make a 32-bit adder? Simple. It is actually made up of 31 full adders. So you have full 1-bit adder here, and then you take in, this is A, and then you take this is 32 bits actually in signal. This is 32 bits. So you take the 0th or the least significant of that. So here there are 32 wires coming in, and then you take the least significant of that and feed it to the 1-bit adder. I go to ALU, but this is adder. 1-bit adder, and then you have another 1-bit adder, and then the C out of that signal, C out of the previous adder is actually connected to the C in of the next adder, right? This is how you make more bit adders, right? I think you have also learned this in the previous digital circuits, but I'm just iterating it. So this is how you make the 32-bit adder, right? So in this 32-bit adder you have 31 of these, I see 32 of these 1-bit adders connected together using these wires, using these internal wires. So these internal wires connect the previous stage to the next one. So here the bit least significant will go, here bit 1 will go of A and B. Similarly here 0th first bit and first bit. Similarly, this is how the internal structure of 32-bit adder is, and then the output is actually connected to here, which is sum, and here this is 32-bit, but the 0th comes from there, the first bit comes from there, the second bit comes from there, and then they make 32 wires, right? This is how you are supposed to make adder in this lab, which is not this way, right? Why not this way? Because now that it is compiled, what I can do is that go into netlist viewer, RTL viewer. Why we don't want you to make it that way is because when you write it that way, the compiler actually does most of the job for you. So the compiler has actually made a very complex circuit which it thinks is very efficient, and it is actually very efficient. But the thing is that we don't want you to rely on the compiler to always make your circuits. Most of the circuits which are there in the outside world are not that easy. You don't have and or these keywords already made up for example Ethernet controller. So if you want to do Ethernet, send out the data, how would you do? Send data, that's it? No, you will have to code it yourself. So that's why we in this lab we actually we want you to make a compound ALU, or more or a more sophisticated ALU, which is composed of smaller components. So here what I'm going to do is make another VHDL file. So this is right now simple ALU. I'm going to make a 8 to 1 mux, 8 to 1 multiplexer. So this is how you make the 8 to 1 multiplexer. So you have 8 input signals, and then you have a select line, and then you have the output, right? And then the architecture of this multiplexer is a process. Any of these signals change, either select changes, input changes, any of these signal changes, then the output will be according to whatever the select signal is. So in digital circuits, this is what it looks like. So what we designed just now, 8 to 1 multiplexer, is actually, this is the select signal, and then you have 8 of inputs. So this is in 0 and up to in 7, and then you have Y. So if select or input signals change, the Y should change as they are changed. There is no clock. This is a not sequential circuit. This is the other type of circuit which does not depend on clock. So as the input or select signal changes, the output should suddenly change at that moment, should change without the clock signal. So that's a simple 8 to 1 mux. Why do we need it? Because we are designing an ALU in which the select is actually our ALU operation. So according to that operation, we are going to select which of these components we need. So what we are designing, why do we need it? We need it because, for example, we have a and, we have or, we have adder. Then we will connect all of those together to the mux, in which we will feed in our opcode, which is operation, what do we want to do, and then here will be our result. So, and then we will feed in A, we will feed in B there, A, B, same goes there, A and B, and then that will be connected there like that. 0, 0, 0, 0, 0, 1, or whatever the lab manual says. This might not be correct. So 0, 1, 0. So according to the operation code, if you have 0, 0, 0 in here, this will, and result will be forwarded to the ALU output. So this is our ALU. So this is what we are trying to design here, 32-bit ALU. My drawing is very bad here. Let me show you what that looks like. So this is what we are designing. So we are designing an 8 to 1 multiplexer, and we have andgate, orgate, adder, a roll unit, and then 32-bit notgate. This is how it all is supposed to be connected, right? And then the output is the output is given out from there. So this as a whole is a ALU. A comes in this side, B comes in this side, and the result an ALU operation from here. ALU operation selects what output we want to route to the out or send out from the ALU unit. So this is actually what you can say is a black box analogy. Inside that ALU box, we have smaller boxes, and then inside those smaller, for example, in 32-bit adder, we have smaller 1-bit adders, 32 of those, and that's how the 32-bit adder is made up of. So this analogy is actually very similar to the programming analogy which we are actually learning in our software courses. In software, you have classes, and then classes in hardware you have entities. So you make entities, and then when you want to make an object of that class, that is called an object. And then in here in hardware you say a component. So you make a component, and a class can have many objects of other classes, right? So, and whatever in software we have a thread or function, that is almost similar to process but not exactly, because process is, as I discussed with you in the lab, is more parallel. It's not sequential as the programming language is. We will understand that as we go through the hardware. So let's go back to the multiplexer. So this is how we design the multiplexer. Let me copy the name of this file, save, and then I'll save it as mux821. So now that we have made the multiplexer, now we need to make a full adder, right? So that we can make a 32-bit adder. So again, file, new, VHDL file, and then we can make in a full adder. So this is a full adder. It has one A, B, C in, sum, out, and then notice there is no process in here. So this not having process is kind of like, it does not depend on any signal, any of these signals, A, B, C in, sum, C out. Any of these inputs changes, the output changes at that same moment. It's a simple circuit with XOR gates and OR gates and AND gates. So this what we wrote here is actually what you get after the Karnaugh map, right? When you do Karnaugh map, after that you get these functions that sum is 1 when A or X or B, the result is with X or C in, right? So that's sum, and then C out. So these are actually the exact functions when you get from the Karnaugh map. Alright, so let me save it as full adder. Alright, now we have full adder. Now we need to make a 32-bit adder, right? Let me again create a new VHDL file, and then adder 32-bit is, instead of here in full adder we had A in, it's a standard logic which means 1 bit, right? Here A in is actually a vector which means it's 32 bits, 31 down to 0, 32 bit, and carry in is actually 1 bit and carry out is 1 bit. Rest all are 32 bits. Output is, result is 32 bits, and both of the inputs are 32 bits. Now when we come to the architecture of this 32-bit, how do we actually connect the inside components? Let me just briefly write this there. Alright, so this is the architecture. Now we know that the 32-bit adder is actually just made up of smaller full adders, right? So what we can do is actually in software we import that class and use it or make an object of that class. Similarly in here you do make a component. So you say component full adder is, and then you actually copy paste whatever that is. So let me do it in front of you so that you know. So I'll remove this, I'll go to full adder. Whatever was the here in the entity, I'll copy it and then paste it here. And remember this, before begin is where you describe the actual architecture. Here you can make objects or something like that in here, right? So here you have entity, instead of entity you make a component, same like object, and then you end not with full adder but component. So here you just describe what are the inputs and what are the outputs of that component, so that this 32-bit adder actually knows what that class is. A class is public functions are similar to public functions, A, B, C in, sum, and C out. Those are public, what are exposed outside. So then we have this signal. Signals are kind of like, remember how I told you that here, let me go and find it. Yeah, here this part, this wire is actually a signal, which means it's an internal wire, right? So you have 1-bit adders, and then they are all actually connected to each other using these internal wires. So these wires, we call them signals. So I actually made a wire, I named it wire, you can name it whatever you like. So I named it wire, and it's actually a collection of wires which goes from 30 down to 0, which means they are 31. So which is what we need actually. So in order to connect 1 and 2, you need one wire. Similarly, you will need one less than 32 wires to connect all of them together. So that's why it's go from 30 to 0, not from 31 to 0. Alright, so how do we describe the how do we connect them together? So I will make a object of full adder, we call it component, and I will name it P1, and then it is of type full adder, and then I will map it, we call it port mapping. So I will map the first input to the 0th of my input. A in is 32-bit adder's input. I will take the 0th wire of it and map it to A of the first adder, P1, and then B in, 0th wire of B in, and then map it to the P1's input. Similarly, C in, and then result. What happens with the C out? Remember how in this we have the C out connected to the C in of the next adder, right? So we connect it to the 0th wire. So for now we are just connecting it to 0th wire. So when we describe the second one, we say A in, B in 1, 1, 1, because the next bit, and then we connect C in. Remember in the previous ones we took C in of the 32-bit adder, right? But in here we took the C in, which is wire 0, same wire here. We took the same C out from the previous state and plugged it into the C in of the next full adder. And then we give the result, first bit of the result, 0th bit of the result, and then we connect it to the next wire. Similarly, you will have to, you will have to do it for 32 bits, something like this. That is our 32-bit adder. Adder 32-bit. Right. So I hope you understand this one, and let's go to the AND gate, 32-bit AND gate. So we make file new VHDL, and then we make the 32-bit AND gate. Save it. Actually, copy that. It's a good practice to actually save it by the name of the entity. So I always do that. Similarly, we do it for 32-bit OR gate. Okay, now we have made AND gate, 32-bit OR gate, 32-bit adder, full adder, 8 to 1 mux. What is left? Right shift, file, new, VHDL file, and then right shift. So this is right shift 32-bit. I'll save it as that same name. File, new, VHDL file. Okay, and left shift. Alright. So, and also remember we need here we also need 32-bit NOT gate and 2 to 1 mux. We already made the 8 to 1 mux, we made the AND gate, we made the OR gate, we made the adder which can do addition and subtraction, we made the ROL, we made ROR, we need to make NOT gate and 2 to 1 mux, right? So we can make a new file, VHDL, okay. This is the 2-bit NOT gate, simple, Y output is not of X, that's it. So not 32. Alright, now last thing is left, which is 2 to 1 mux. In 0, in 1, it's the same as 8 to 1 mux, just the inputs are less. They are also 32 bits, but just 2 inputs, and then if it is 0, you give the first one. If it is 1, you give the second signal out. While others, Z, this Z is actually high impedance. High impedance means, for example, the wire is actually disconnected, which means that air has high impedance. When two of the terminals of the battery are very far apart and disconnected by the battery by the air, it's high impedance, which means there is no ground. Ground means it's connected to 0 volts. 1 means it's connected to 5 or 3.3 or whatever the high level you select, and Z actually means the wire is disconnected, or very high impedance or very high resistor is connected, like almost 0 current is flowing through, which is the same as air. Air also has some kind of resistance, but it is very high, so current can't flow very freely through it. So we will save it as mux 2 to 1. Alright, now that we have all the components we need, we made all the entities. Now let's make the complete circuit. And make a new file, and then we have the compound. I called it compound ALU because it's made up of smaller components. You can name it whatever you like, and it has A, it has B, which is 32 bits, and operation is 3 bits. Result is 32 bits. Carry out is 1 bit. 0 is 1 bit. That's a flag. And then we have begin here, begin, and then we have end ALU implementation. Right? Compound ALU. So also, it's a good practice to actually keep it tagged proper way so that you know where the thing ends and where it begins. Alright, so as I did for the a full adder, internal components are described before the begin statement. So here I will describe the 32-bit. It's actually this thing is actually same as entity. Instead of entity we write component, and instead of the name of the component, for example, if I go to the adder 32-bit here, I just copy paste it from here and then paste it here. After you do paste, make sure end is aligned with the entity, and then entity, make it component, and then paste it here too. That's it. That is your description of the 32-bit adder. So this is how you make the object of those things, object or component of those things. So similarly, we describe all the components we made, whatever we want to use inside the 32-bit ALU. We describe that. So we have 32-bit AND gate, 32-bit OR gate, same component, end component, logical shift right, logical shift left, 8 to 1 multiplexer, 2 to 1 multiplexer, NOT gate. Right now, after the components, before the begin, keep in mind before the begin, we can describe also the some of the internal wiring which we want to do. So here I have the AND result wire, OR result wire, adder result wire, LSL result. LSL is logical shift result. So these wires are actually connected to the outputs of these components, and then I will finally connect them to the multiplexer and then send it outwards. So these are the internal wires which I described. Inside the begin, we port map. So inside the begin, we can actually write in. So mux1 is the object of 8 to 1 multiplexer, and I want to map its port to. You can also write it like this way. In 0, I want to assign it to AND result. In 1, OR result. In 2, adder result. Why in 0 and 1? Why those specific things? You have to look it into the lab manual. So in the lab manual, 000 is actually in 0, right? So in 0 should be connected to AND result. OR result is in 1, which is 0 0 1. So same, if I open up the lab menu again, 0 0 1 is OR. So 0 0 1 is OR. Adder is that, and again adder. You have two of these adders, and then where you decide whether this is addition and this is subtraction, you do that in the NOT gate and connect the B negative decider multiplexer. So this is the 2 to 1 multiplexer, which is as we described in here. This one, we need to connect B directly to the 0th one, and then B should be connected to NOT gate, and then NOT gate's output should be connected to the first part of it. So that is what I did here. So in 1 should be B NOT signal. B NOT is actually a wire. B NOT is a wire. So I connect in 1 to B NOT, which is the output of this NOT gate. So B feeds in, B NOT comes out, and that wire is connected to the in 1 or the multiplexer. And that's all for this lab. I hope you understood it. Let me see if it compiles successfully, and hope to see you for the next session. And hopefully this video helped you in figuring out how to do the lab 3A. See you in the lab, and if you have any questions, please, even if you are not from my section, please do not hesitate to ask me any sort of questions. Thank you.